Now that we've talked about the executor framework as a whole, we're going to start zooming in on each of the interfaces one at a time, starting with the executor interface, which is mind-numbingly simple, so this won't take very long to go through. So what we'll do in this part of the lesson is just talk about the simple and single feature that's provided by the executor interface, and then in the next part of the lesson I'll show you an example that brings it to life and hopefully makes it more interesting. So as I talked about before, the executor has a single method that's used to provide a new task or new task for execution. Very simple-minded intentionally. Each task implements the Runnable interface. You've seen Runnable a gazillion times before at this point. Runnable is the same thing, of course. It's provided when you make a new thread and start the thread. You have to give it a Runnable or a Lambda that stands in for that Runnable. And essentially, what the Runnable does is it defines a command. And a command in this context is using the term from the command pattern from the Gang of Four book. Hopefully you've been exposed to that in other courses. So a command is basically an object that's used to encapsulate all the information that's needed to perform an action or trigger an event at a later time. So in this particular case, the runnable command is going to encapsulate the behavior that will be run typically in a different context, typically in a different thread. Although if you use the single thread executor, it'll run in the main thread, which is kind of weird, but that's why we kind of view that as a pathological special case. Typically, these runnables are commands that run in a background thread. As we mentioned before, a runnable is a one-way task, so it does not return a result. Obviously, you can get results back, but it's not going to be through the interface of the runnable. It'll be through some other means, and I'll show you some examples here in a minute of those other means. You can execute the runnable in the background thread, which is 99.999% of the time, or in the main thread. And of course, the way that you dictate which it does is based on the implementation that you configure when you make an instance of the executor interface, which is often, although not always, done via the factory methods in the executor's utility class. Under the hood, this particular interface implements the command processor pattern. So that's a pattern that appeared in one of the Pattern Software Architecture books, Volume 1. And the command processor pattern basically packages functionality into an object and allows that object to be reused later in another context. In this case, the context is typically a different thread. Or if you're using the scheduled executor service at a different point in time in a different thread. So the idea is you package things up and you hand it off to a command processor. You package up a command and you give it to the command processor, and the command processor then executes it later. Very, very, very common pattern in concurrent programming, used all the time. All right, so that's the end of the Java Executor interface discussion. Again, it's so simple, we didn't need to spend much time on it. Okay, now that we've talked about the mindlessly simple executor interface, let's talk about how we could actually use it to solve a problem. And the example I came up with here, which I've uploaded to GitLab or GitHub, and I'll show you the URL in a second, is a prime checker app. And we're going to use the executor interface in order to check whether numbers are prime. So we're going to use this. We're going to generate n random numbers, and we're going to use the executor framework to determine whether the numbers are prime numbers or not. And I'll explain in a second why I chose that particular example. I'll run the program for you in a minute. This is what it looks like, or here's a snippet of a run where I'm checking 25 random numbers to see if they're prime. You can see occasionally they're prime, often they're not prime. And if they're not prime, it tells you what the smallest factor is to multiply to get that number. And you can download the code here at this link. Okay, there's a couple of classes in here that we're going to talk about. So first of all, the reason I chose prime numbers is I was trying to think of an example where it would be compute bound, and therefore there would be a benefit of being able to transparently tune the number of threads devoted to the running of the program without affecting the way the program was actually written. So as we're going to see here, and this is the benefit of the executor framework, remember our goal is to decouple the concurrency and the amount of threads we're using from the application logic that's submitting work to be processed in parallel. So here we're going to basically create a new fixed thread pool that has as many threads as there are processor cores on the device. So there's a method called available processors, which you can get from the runtime class of Java. And so if you're on a multi-core machine or a quad-core machine or a hyper-threaded machine or whatnot, this will return to you the number of cores. And so we're going to make ourselves a fixed thread pool with that many cores. And so the cool part about this is if I run this program on a 2-core machine, it'll have 2 cores, transparently. If I run this program on a 4-core machine, it'll have 4 threads, transparently. 8 cores, 8 threads, et cetera. And so it'll auto-tune itself based on the number of available processors, processing cores, or hyper-threaded processor cores. And my application code, as you see, doesn't know, doesn't care. It just submits tasks, and they'll be run at sort of the optimal level of concurrency. So that's why we're doing this. OK, so we then have a method, or sorry, a class called prime runnable, which is a runnable, as you might guess from the name. And it's got a public method, of course, called run. And it's also got this method called isPrime. And what isPrime does, it's not the world's most efficient way to compute prime numbers. In fact, it's deliberately brute force to burn up CPU time just to make the thing run for a while. And what it does is you give it a number that's the candidate, the prime candidate, and it starts basically typically at 2, and it goes up to n divided by 2, and it takes the number n and it divides it by the factor, 2, 3, 4, 5, 6. It divides the number, divides n by the factor, and then it multiplies by the factor, and it checks to see if it gets n. If it gets the number back, it's not prime, right? If you go through all of the factors from 2 to n over 2, and it never returns the number, then it's a prime number. Now again, this is not the world's smartest prime number checker. If you take a look at Wikipedia, you'll see lots more insightful and efficient ways of checking for primality. But I just wanted to have something that would burn some CPU time and do something interesting. All right, now here's where things get fun. And I'm going to show you this code, and I'll explain it. And then we'll come back later, probably Monday at this point, and I'll give you some more background on Java 8, because we've used it a lot, but I haven't really talked about it in detail. So this piece of code will generate count random longs from 0 to max int, max value of the integer. And then for each of those random numbers it generates, it will go ahead and create a new prime runnable with that random number, passing in the, this is a lambda expression, so it's going to take the random number that came back from each of these count number of random numbers, and it'll go ahead and create a new prime runnable with that random number as a parameter, as you can see here. And this, which is, of course, the activity that we're calling this on. I'll talk about why we need to pass that in a second. And then we're going to take that runnable and we're going to execute it. So let's say we have, 50 random numbers that we want to check for primality. Then we're going to go ahead and generate 50 prime runnable objects and execute them. But keep in mind that the number of threads that we actually have running concurrently is a function of the number of cores on the machine. So this piece of code here doesn't know, doesn't care about that, right? It just says, I'm going to create count runnables and execute them. And then we can use the available processors method to transparently tune the number of threads that are actually run. So based on your hardware characteristics and your system, that number will change. But we didn't have to hard code that into the application. That's the key thing that you want to recognize from this. We can transparently tune the number of threads independently of the code and the application that's using those. So the code here is just making tasks, which are runnables in this case, and throwing them out to be processed. Any questions about that? OK, so we click on the floating action button. Let's give it a number like 10. I'm going to generate 10 random numbers. That didn't take very long at all. Let's give it a slightly larger number, like how about 25? That's a good one. You'll notice, by the way, that none of these numbers were prime. And that's significant because if we run it again, you'll see whenever there is a prime number, it takes a lot longer to run. I don't know if you noticed what it did. I'll try to run it again. Actually, let me give it a much larger number that will take a long time to run. Let's give it 100 numbers. So you can see that it's now blocked. And whenever it kind of blocks, that's because it's computing, it's checking, and the number is a prime number. So it has to go way through those factors. And so it takes a lot longer to run. So it's still chugging away. It finally finished. So what I want to show you now is a couple of interesting things. So this program is using the executor interface, which is very limited. And so now what I'm going to do is I'm going to start running this computation for a large number of things, and I'm going to go ahead and rotate the screen. And you'll see something weird happens, undesirable happens. So we start running. You can see it's stuck somewhere on a prime number. We rotate the screen, and that is the end. So what's happened in this case, and when we look at the code, it'll be more clear, because of the wacky limitations and constraints of the executor framework, it's very difficult for it to figure out how to handle screen rotations properly. So it can lose messages, and other weird things will happen. So let's take a look at the, first we'll take a look at the prime runnable. So prime runnable implements runnable. It stores the prime candidate, the number we're going to evaluate for primality, in a field. And it also stores the main activity in a field. You'll see why we need to do that in a second. Here's the isPrime method. And here's the run method. So what we do in this case is when run is called, that run gets called, of course, when this task is ready to execute, when it's first in the queue, or if it's the only one there. So we go ahead and we compute whether it's prime, and that gives back the smallest factor. If the smallest factor is non-zero, then it's got a factor, so it's not a prime number. And you can see that we go ahead and we use mActivity in order to be able to tell the main activity the result. So we're communicating the result back to the main activity by making a call that goes to an activity that we had to stash away in our runnable. And if it doesn't have if it has the smallest factor that's 0, then it is a prime number. And the last thing we do is we tell the main activity that we're done. The reason we have to do all this stuff is because we have to do all this stuff here is because Runnable is a one-way method. So a runnable task doesn't have any other way to get a result back. So what we have to do is we have to give it something that it can use to communicate back the result to somebody else, in this case, the main activity. And you'll see when we talk about evaluating this thing, that's somewhat limited for a variety of different reasons. OK, so that's basically what this code looks like. It's not complicated code, but the subtlety to remember is you can't get a result back any other way than to communicate it through some sort of out-of-band mechanism, like passing a reference to the activity. Here's the main activity. A lot of this stuff is pretty typical. We have an executor here. That's a new fixed thread pool with the number of available cores. This is going to be stashed here. This code is boilerplate code. We've looked at this before. When someone clicks the start button, we figure out the number of computations to run. We start the computations. It comes down here, does a little sanity checking, and so on and so forth. And I've also got this thing called mRunningTask. This is the other hassle with the executor framework. There's no easy way to know when you're done, and so you have to explicitly keep track of things to know when you're finished. Now, we could have used a cyclic barrier or a countdown latch or something. I didn't want to show that in this example. So all I do is I simply have an atomic integer called mRunningTasks, and once I know how many tasks I'm going to run, I give the count. And then, as you'll see, when this thing runs, every time it gets done, it decrements by 1. And that's how it knows when it's finished. So down here, we go ahead and we make a new random object. And then we use the streams mechanism to make a stream of random longs with count elements from 0 to max value. We'll talk a little bit later about what streams are. But for now, just think of them as a stream of values, kind of like a video stream. And for each of those random numbers, we're going to execute a new prime runnable with that random number, and this being the activity that we have. OK, so that's basically how we get things kicked off, right? So now they're all running, and at any given point, typically 2 of them are running, because this is, say, a dual-core machine, or 4 of them are running if it's a quad-core machine. Here's the done method. Remember, done gets called here inside of run when we're finished with this computation. And you can see what done does is it comes in here and it uses our atomic integer and it decrements the atomic integer by 1. Why do we have to use an atomic integer here? What's the reason of using an atomic integer versus just an int? Right. The done method is being called in the run method of a runnable, which in this case is running in a background thread. So we have to make sure that whatever we're doing here is atomic with respect to the operations on it. So this will go ahead and atomically decrement the count. And when the count drops to 0, that means that was the last one. So what we do then is we make ourselves a little command to finish things up, and we go ahead and run that command on the UI thread. OK, so that's basically the implementation of this thing. Here's the print line method that's just used for the background tasks to print their status to the UI thread. And we have an onResume method, which, oh, I know. That's right. So remember when I rotated the phone and it still continued to run? The reason for that is it restarts it when it rotates in this case. So I'll explain in a second why I had to do that. But that's why it appears to keep running, because it's restarted, which isn't really quite the right semantics, but at least it makes it look like something is happening. So now that we looked at the code, let's go back and evaluate this app and talk about what's good and bad about it. So the good part, and the reason for using the executor interface at all, is that the number and the type of the threads can be transparently tuned with respect to the rest of the application logic. So here's the application logic. This is what main activity was doing. And under the hood, we could have chosen all kinds of different thread pools with different numbers of threads and so on. Those things could have been done in different ways, but this piece of code here wouldn't care, because we've decoupled the interface from the implementation. That's the benefit of using the executor interface. Sadly, however, there aren't many other benefits of using the executor interface, because it's sort of very lame and limited. It restricts things overly much. That's my icon of restricting and compacting the application. So one of the problems here is that the runnables have one-way semantics. And one of the consequences of the fact that they're one-way is we end up overly coupling the prime runnable with the main activity. So you can see here that we had to pass the activity here into the prime runnable. Why is that a problem, you ask? Well, the reason it's a problem is that when the runtime configuration of the phone changes, when someone rotates the phone, what happens? The activity is destroyed. However, there's no way of being able to tell this runnable that that activity has gone away. So as a result, it'll just sit there and continue to run, but it won't output anything anywhere. It'll just evaporate into nothingness, like going to dev null. And that's because there was no way for us to get access to reset that runnable, or no convenient way. We could have, there's ways of doing it, but it would have been unbelievably convoluted and costly and inefficient. And that, again, is because of the one-way semantics. And you'll see when we show you the two-way semantics later how we can clean that up in a nice way. So that's one of the problems, that you're tightly coupling things that probably shouldn't be coupled. The second problem is that there's no lifecycle operations on the Java Executor interface itself. Does anybody know what this is? I mean, obviously it's the no sign, but what's behind that? That's the Sanskrit symbol for samsara. Does anybody know what samsara is? It's the Buddhist and Hindu concept of rebirth and reincarnation, life cycle, right? Coming and going, birth and death. So there is no support for lifecycle operations with the executor. You can only execute things. And that has some problems. One of the problems is you can't interrupt or cancel tasks that are running, because we have no way to get to them, right? We don't have any access to those threads, and there's no way to shut the executor down itself, because there's no method to get to it to tell it to shut down. So that's kind of bizarre. We can't clean things up. If we turn the phone, then there's no way to stop those threads. They'll just keep running, but they won't print anything out, which is disturbing. And the other problem is you can't gracefully handle runtime reconfiguration changes. So you can't handle changes, so changes don't happen appropriately. All right, so that's the end of that discussion.